Welcome back. Now we will start talking about the effect of moisture on the resilient modulus, which is characterized using the soil water characteristic curve. Typically for a soil, when we are trying to compute any parameter, what are the basic parameters that are required for computation? So one is the maximum dry density given by gamma d max, the other one is specific gravity, and the third one is optimum moisture content. So if these three parameters are known to us, which is the maximum dry density, the specific gravity and optimum moisture content, then we will be able to compute any other parameter related to soil which is required to compute its influence on modulus. Now, so all other mass volume parameters can be computed based on these three values. So it is primarily focused on influence of moisture on the modulus of granular layers, right. This effect of moisture on granular layer, like we said, is going to is classified into three different aspects. One is the influence of moisture on the stress state. So when the soil is in a dry condition, the stress state in the soil is different compared to it in a moist condition. So you should have already learnt about all these things in the previous lecture. The second one is the influence of moisture on the modulus variation, right. So moisture or density on the modulus variation, and the third one is the freeze and thaw effect. So these are the three common effects which are typically defined. Here in this reminder portion of this lecture, we are going to talk about the influence of modulus on the we are going to talk about the influence of moisture on the modulus variation. So this relationship, the influence of moisture, is given by a soil water characteristic curve, which we typically call as SWCC. It is basically the relationship between amount of soil in water and the soil suction, right. So when, let us say that a system of soil is present, so there is one soil particle here. What is the capability of this soil particle to absorb moisture which is present in this environment, right. So that is quantified through this soil water characteristic curve. There are many definitions, many kind of interpretations which people make for this particular parameter. In another context, it is also defined as the variation of water storage capacity within the macro and micro pores of a soil with respect to suction. So if it is able to absorb some amount of, if it is able to suck some amount of moisture from the surrounding, how much of it is it able to withhold in the micro and macro pores of the soil, right. So that is another interpretation which certain authors make to the soil water characteristic curve. Ultimately, it is a key information which is required to analyze seepage, shear strength and volumetric problems. If you look at this, it basically says how much water it is able to absorb and how much of the absorbed water it is able to retain in the pores, right. So this is what is going to influence the seepage characteristics in a soil. Similarly, depending upon the moisture content that it is able to retain, the shear strength of the soil is going to vary. Again, it is also going to influence the volumetric aspects of the soil also. So that is why this particular information is sufficient, is considered to be sufficient for representing the moisture aspects of soil. In some studies, it is also called as a water retention curve, because we said it is going to quantify the storage capacity within the pores. So it is also called as a water retention curve. Now what is this soil water characteristic curve? It is basically a plot, right, wherein the water content expressed in percentage as a function of soil suction. So it could be in kilopascals or megapascals, whatever be the unit. So it is a graph between soil suction and how much of this it is able to retain, right. So this can be expressed in terms of gravimetric water content or volumetric water content or degree of saturation, right. So what is this gravimetric water content? This water content is expressed as a ratio of mass of water to the mass of solids. So that is the gravimetric water content that is defined. Similarly, what is the volumetric water content? It is defined as theta, which is nothing but volume of water as a sum of volume of voids and volume of solids. So this is volume of water, this is volume of voids, and this is volume of solids. So, this is quantified as volumetric water content. So, ultimately what is degree of saturation is defined as volume of volume of water to the volume of voids. So, in my voids what percentage of my voids, again we multiply into 100. So, what percentage of my voids are filled with water? If all my voids 100% is filled with water, then we call the degree of saturation to be 100. If there is a lesser percentage, then we associate a lesser value. So, this is what is called as the degree of saturation. So, these are the 3 parameters which could be used on the y-axis. Either of these 3 parameters will be used on the y-axis with respect to soil suction. Some textbooks also call this as metric suction, right. Now, how does this soil water characteristic curve look like? You can see here, this is volumetric water content and this is metric suction. Again, there are other kind of interpretations also available for this soil water characteristic curve. One is the amount of energy required to remove water from the soil. This is one kind of interpretation. How much of an energy is required to remove a water which is present in a soil system, right? And the other interpretation is, in the soil in a dry state, how much force it exerts to attract water, how much pressure it exerts to attract water from a nearby location. So, these are 2 other interpretations which could be given for this soil water characteristic curve also. So, typically what is said is, when the soil is flooded with water, when there is more amount of water, when it is in a saturated state, the metric suction will be very less. Say for example, let us take the condition of a sandy soil. You can see here, when there is 40% volumetric water content, let us say, when there is 40%, the metric suction is very less, about 1 kilopascal of force only it is exerting. Okay, we can interpret it in any way. We will say that the amount of we will use this particular interpretation, which is amount of energy required to remove the water film from the soil particle. Now here there is up to 40%, there is only 1 kilopascal of force which is required to remove this water content, whereas once the volumetric water content reduces, we also we have to apply a higher amount of force to remove this water from the soil system. If we use the other interpretation, which is the force exerted by the soil particle to attract moisture, that would also be valid for this particular graph. If you see, when it is kind of saturated or when it has more amount of water content, there is the force that it is applying to attract more moisture is less, right. But in another scenario, when it has 20% of volumetric water content, we can see that it exerts more force to attract water content, right. So, this is the interpretation of this soil water characteristic curve. You can see here, depending upon the type of soil, this SWCC curve is going to vary. So, for a sandy soil, you can see this remains constant up to 1 kilopascal metric suction, whereas here it is linear up to, let us say 50 kilopascal metric suction. So, up to when the water content is 60%, when the volumetric water content is 60, you can see here it remains constant up to a metric suction of 50. Beyond that only it begins to increase. Similarly, for a clay soil also somewhere closer to that. So, depending upon the type of soil, this curve is going to vary, right. Similarly, we can also see how the soil water characteristic curve varies for different kind of the state of soil. So, we have a compacted specimen, which is a typical laboratory compacted specimen. We have an undisturbed specimen. We have a slurried and then pre-consolidated. So, we have the soil in the form of a slurry state. We have a soil which is slurried in the initial condition itself. So, depending upon for a given soil, depending upon the state in which the soil is present also, this soil water characteristic curve will differ, because in a slurry state the state of soil is different, the movement of moisture content will be different compared to a fully compacted state. So that is why for a given soil also, depending upon the state in which the soil is present, the soil water characteristic curve will differ. So this could also be expressed in terms of degree of saturation. So when the degree of saturation is 1 or when it is 100%, the metric suction is very less, right, then it increases, you can see here, and then towards the, when the degree of saturation is very less, this value is substantially higher. Again, depending upon the gradation of the soil, this is for a soil which has a D60 of 0.1 mm and this is for a soil which has a D60 of 0.4 mm. So depending upon the gradation of the soil also, this is going to vary, right. So this is highly sensitive to the type of soil, the natural condition of the soil and the particle size distribution of the soil. So this is with regard to the soil water characteristic curve. So this soil water characteristic curve depends upon 3 parameters. One is the plasticity index, the other one is the percentage passing 200 number 200 sieve. This number 200 is nothing but 75 micron sieve. And the third one is effective grain size corresponding to 60% passing by, which is nothing but the D60 value. I hope we all know what this D60 value is. If we plot a cumulative percentage passing versus size, so this will increase like this. So we will take 60% here, drop it down. So this will be the value corresponding to D60. I hope we all know this. So this is the other parameter which will govern the soil water characteristic curve. So depending upon all these parameters, other parameters could be computed. So what are the computed parameters? Previously we said we need 3 other inputs for soil. For any soil characterization, we need the maximum dry density, specific gravity of soil and the optimum water content, right. In addition to these 3, if we know the plasticity index of the soil, if we know the percentage passing 75 micron sieve and if we know the D60 value, we can compute the parameters for a soil water characteristic curve. So what are the other 3? One is the optimum volumetric water content. So it is calculated like this: optimum into gamma D max by unit weight of water. Similarly, we can calculate the initial degree of saturation, which is S optimum. This depends on the optimum volumetric water content, maximum dry density, unit weight of water and specific gravity of solids, the soil. Then we also can calculate the saturated volumetric water content, theta saturated, which also depends on the optimum and the optimum water content and the initial degree of saturation. So depending upon all these things, we will know to what extent the soil is saturated and we will be able to compute the appropriate influence on the modulus value. Now we will see what is the effect of moisture content in soil on the modulus parameter. So there is an equation which is given, again this is from MEPDG, which helps to correlate the resilient modulus at any given moisture content to the resilient modulus measured at an optimum moisture content, right. You can see here MR by MR optimum is the resilient modulus ratio. MR is at a given time and MR is the resilient modulus at a reference condition. So at a given time means at any given time period in a year, which is going to vary with respect to moisture. At any given time period in the year, we are going to have influences of moisture. So that is one effect, and the MR optimum is at any given reference condition, which could be for the optimum moisture content or any standard moisture condition. And A is the minimum value of log MR to M optimum and B is the maximum of a log. If we have a log graph of MR by M optimum, it is the maximum value. I have plots, I will show you what this is. Km is a regression parameter, and S minus S optimum is the variation in degree of saturation. This is the optimum, S optimum we have defined earlier, right, initial degree of saturation which is given as S optimum, and this is for any given saturation. Okay. So, based on this the variation in modulus is computed. We can compute MR by MR optimum. So, we know what is it at a reference condition. So, for the given condition we will be able to compute the resilient modulus. So, this is how it is computed in MEPDG. So, this equation which was shown previously, this equation which is shown here approaches a linear form for degree of saturation S, any given degree of saturation which is within plus or minus 30% of the optimum value. So, let us say this is my S optimum. So, whether it is this side 30% or this side 30%. Okay. It is 30% on either side, it has a linear form. Okay. But if it is less than 30%, it flattens out, that is for degrees of saturation which is lower than 30% below the optimum value. If you look at this graph, you will be able to understand. This is for fine grained materials, this is the ratio which is log MR by MR optimum, and this is S minus S optimum. So, if you see here up to 30%, so this is 30%, again approximately 30%, it has a linear form. This side also you can see here up to 30%. So, in this range with plus or minus 30%, it has a linear form, but if it is less than that, it kind of flattens out. For all the other cases, it is assumed to be a constant value, right. So, this is how this model is proposed, and this model is used in MEPDG to adjust the resilient modulus depending upon the moisture content of the soil. Similarly, we have another graph for coarse grained soil. You can see here the ratio is 0.3 here and this ratio is 0.4. So, the influence of moisture is more on the fine grained soil when we compare to a coarse grained soil, right. And we can see here the values of A, B and Km for coarse grain and fine grained soil for this particular equation which is given here, right. So, you can see the value of B, which is what we defined which is what we defined here. This is the value of B, which is the minimum of log MR by MR optimum. So, this is 0.3 in the case of coarse grained material and 0.4 in the case of fine grained material, and A is different for both the materials and also the regression parameter, right. So, using this kind of an equation, we will be able to correct the resilient modulus for any given moisture content with respect to the moisture content at a known standard condition. So, ideally we could use the optimum moisture content, measure the resilient modulus corresponding to the optimum moisture content using the codal provisions that we had discussed earlier, and once we have these values and input in the system, we will be able to compute it for any other moisture content. The only thing is we should be able to compute the appropriate degree of saturation, right. So, that comes from the soil water characteristic curve. Now, we will see what are the effect of some other variables on the modulus measurement. We can see this plot, these are all taken from Durham et al. In their study. You can see here what is the effect of variable on material modulus. So, the first one is at a saturated moisture content and at optimum moisture content, what is the effect of resilient modulus on deviator stress. We have seen what deviator stress is. It is the axial stress that we apply during the measurement of resilient modulus, and it is a stress which is over and above the confining pressure in case of a confined test, or if it is an unconfined test, it is simply the axial stress. You can see here as the deviator stress increases, the resilient modulus decreases. If you recollect, in the previous lecture we have seen that as the confining pressure increases, right, as the confining pressure increases, the resilient modulus was seen to increase, right. So, this is with respect to confining pressure. On the other hand, if we have deviator stress in the x-axis and if we have resilient modulus here, it is going to decrease as it is shown here, right. Again, the degree is going to be different for a saturated case and for an OMC case. When in a saturated condition, right, when it is fully flooded with water, the resilient modulus is lesser compared to that measured at an optimum moisture content. So, you can see there is about a 2 times difference in modulus between the optimum moisture content and the saturated moisture content. So, this is the first parameter, which is the influence of the moisture content present in soil. The next one is the influence of confining stress. So, we can see again this is all from the resilient modulus test that we had discussed earlier. So, only in a laboratory condition we will be able to precisely specify these numbers and quantify the effects. So, we said we are giving different confining pressures. If you remember the loading sequence, we had different confining pressures. So, one is 13.8, 27.6, 41.4. So, for each of these cases, how the resilient modulus varies with deviator stress. You can see again with deviator stress it decreases. It is not a linear variation, we can see that as well, and it is also varying with confining stress. Let us take one deviator stress which is 2 kilopascal. So, this is a confining pressure of 13.8, this is 27.6 and this is 41.4. So, you can see here as the confining pressure increases, the resilient modulus also increases, right. So, this is very important when we are doing the design. It is not only from the moisture perspective, but it is also from the pavement design perspective. Let us say we have a granular layer which is of 200 mm thickness. Hypothetically, let us assume something like this, right. Now, the confining pressure that is experienced by a point which is present, let us say at 50 mm from the surface, is different from the confining pressure experienced by another particle which is present at a 50 mm from the bottom, right, because the depth of the pavement above these 2 points are completely different. So, because of this confining pressure, the resilient modulus will vary, but ideally what we do is we treat this as a single layer and carry out the design, right. So, this point, let us say that there is a pavement system here. So, this point is going to have more load, more confining pressure. So, this point will have a slightly higher resilient modulus compared to this particular point. So, whenever we attempt to measure the resilient modulus, it is very important that we take into account of the confining condition and try to simulate it as precisely as possible. So, this is the influence of confining stress. You can see here when compared to the confining stress, the influence of deviator stress is significant. So, this varies from 13.8 to 27.6 and 41. So, we see about this is let me say this is 70,000, this is 85,000, there is about 15,000 kilopascal variation, but whereas if you take let me assume this to be 15, 25. So, for 25 units variation in confining pressure, there is a 15,000 variation in kilopascal, but if you see here, let me take 70 and let me take 40 for 7. So, for 5 kilopascal variation in confining stress between these 2 points, the effect of resilient modulus is about 30,000 kilopascal. So, compared to the confining stress, the deviator stress is more, the resilient modulus is more sensitive to this deviator stress, right. So, again it is the load that is coming onto the pavement is having a more is having a higher influence compared to the confining condition. And this is also defined differently for different kind of materials. This is the same plot which is for a saturated clayey gravel at a confining pressure of 17 kilopascal, right. So, we can see the variation. We can see a similar one for a So, this is for a saturated clayey gravel. Depending upon the type of material, this relationship will again vary. Now, let us see what is the influence of resilient modulus on the water content. So, ultimately that is what we are interested in quantifying, right. So, as the water content increases, we can see here this is about 5 from 7% here. As the water content increases up to 19%, we can see right. There is a substantial variation in resilient modulus. So, if I call this as 20, this is, if I call this as 30,000 kilopascal, and let me call this as 1 lakh 30,000 kilopascal, there is about 1 lakh kilopascal variation for a water content from 7 to 19%, right. So, as we mentioned earlier, moisture content is having a significant effect on the resilient modulus. So, this is the effect on lean clay. Similarly, we can quantify the effect on clayey sand also, right. We can quantify similar numbers, 7% here, 19% here, identify these 2 points. Right, identify these 2 points and quantify the effect. So, we are getting about a similar effect of 1 lakh, but depending upon the type of soil, the sensitivity also will vary, right. So, this is from the experimental condition. Similarly, we have it for a clayey gravel, right. For a clayey gravel system also, the effect of moisture content is quantified. Now, these are all tests carried out under laboratory conditions, right. Now, we will move into some field data which people have measured to quantify the effect of moisture on the different variables in a pavement system. So, this study, which is by Ahmed et al., is carried out at a location in Dallas, Texas. I am not able to recollect the specific highway number, but if you look into this reference, you will be able to identify the specific highway on which they have carried out this test. Again, I recollect that the soil that is used is clay, right, that was present in that location is clay. Now, in this location, they have captured the moisture content, right, as a function of rainfall. If you look at these black bar graphs here, this shows the amount of rainfall received at that particular location from March 2014 to March 2016. They have collected the data for a period of 2 years. So, for this 2-year period, you can see how the rainfall pattern has varied. The corresponding moisture content is also measured. It is at different depth, 1.2 meters, 2.4, 3.6 and 4.5 meters, right. Now, if you see at 1.2 meter, you can see how much is the variation, right. This red line here, this data is not available for many locations. If you see at 2.4 meter, you can see when there is a higher rainfall, when there is more precipitation, the moisture content has proportionally increased, reduced, and then it has increased again when there is rainfall, reduced again during the dry spell, and then kind of varies. So, we will not be able to specify a particular pattern for this variation, but we can see that it more or less varies with the precipitation. So, if you look at another depth, which is 3.6 mm, there is also fluctuation because of the precipitation. Here you can see it is higher, it is lower, then higher, and so on, but it is not as sensitive, or it is not fluctuating as much as 2.4 meter depth, right. Similarly, if you look at another location 4.5 meters, which is far away from the surface, you can see here that it is almost a constant, right. It does not vary as much at all, or it is almost insensitive to the rainfall. So, this is one important information which they had quantified. It is not the effect of moisture is there on the pavement, but the influence varies across the depth of the pavement. Also, the effect of moisture variation was quantified using an indirect measurement was obtained using the resistivity measurements. So, at different depths they were able to measure the resistivity of the soil, and this resistivity is considered to be indirectly proportional to the moisture content in the soil. You can see here, this is the resistivity which is measured for soil, and this is the depth, right. So, as the depth increases, let us take one particular case, this brown line here which is at a different depth. Let us take this brown line which indicates the resistivity in a particular season. Again, each of these lines correspond to different periods over these 2 years, right. It is again from the same study. So, you can see here in this brown line, for a given moisture content, the resistivity increases and then it decreases, kind of something like this, Okay. So it is for different spells. So this is maybe the resistivity is very low, maybe this is in a wet period. The brown line I can say it is during a wet period, and this blue line I can say it is something during a dry period, right. So during this wet period, let us compare these two lines alone, this brown line here and this blue line here. So during the wet period you can see it has, the resistivity has increased, which means that the moisture content is very low at this particular point, right. It is high here, that is why we get a low resistivity, and as the depth increases the moisture content has reduced, resulting in a high resistivity, and as we go further the moisture content has further increased, causing low resistivity and so on, right. Similarly, we can see a similar pattern for different other periods in the year also. Okay. So this shows that the change of resistivity is very low after 3 meter or 10 feet depth from the surface. You can see here the resistivity here varies from 5 to maybe about 23 or 24. Once we reach a particular depth, the variation in resistivity is very small, right, maybe not even 5 ohm meter. Okay. So this shows that beyond a particular depth the effect of moisture is insignificant, and only up to a certain depth we are able to see significant difference. This is what we had seen from this plot also, wherein at 4.5 meter depth it was almost insensitive to variation in rainfall data. Similarly, there is another study which was carried out by Ohio Department of Transportation. They had taken a strategic highway research program data. So if you recollect, in 1994 the strategic highway research program data was published. It has a lot of pavement cross sections which was studied, and they collected a number of data points across different highway. So this is one particular highway which is US 23 in the Ohio, collected by Ohio Department of Transportation. 40 test sections were chosen, and these were the data that were collected from these 40 test sections. All these purple lines given here, the seasonal pavement response was measured for different seasons. The parameters, different parameters like moisture, temperature and all this data was measured. And the pavement response, the structural response of the pavement was collected at these points which are indicated in the blue square, and in some cases there was no instrumentation that was provided also, right. So this was the test section from which data was continuously collected. Again they have documented a different set of parameters. The first one, or the more common one, is the relation between precipitation and degree of saturation. Again if you see here, this red line is the precipitation and this blue line is the degree of saturation. It is again over an accumulated time period. They have collected it for 1800 days. Right. So for some continuous 1800 days this data was collected. The exact time period is given in this particular reference. So if you look at this, initially the precipitation increases, so the degree of saturation also increases, and once the precipitation reduces the degree of saturation also reduces. So you can see it is more or less in line with the precipitation data. So like as seen earlier, the degree of saturation has a very close relation with the precipitation data, but we should also remember that this relation is valid only up to a certain depth. Beyond a certain depth it is highly insensitive to the precipitation data. Similarly, they had another information which is about the volumetric moisture content which is present and the water table depth, right. So for that particular case they had collected data at different locations. It is in the base, subgrade layers and all that. We can see here that as the water table depth has varied from 1.5 to 2.5, 3, 3.5, there is almost insignificant variation. The line kinds of remains flat. So for this particular case they were not able to obtain any correlation between the water table depth and the volumetric moisture content. Another plot which talks about the saturation, the degree of saturation over again a longer time period of 2500 days is given here. You can see here this we will, if we correlate it to the precipitation data, we will be able to see nice trends here. So for different seasons we can see, so as in a rainy season the degree of saturation is 100, then there is a dry spell, it keeps reducing, and again when there is precipitation it increases, and so on, it fluctuates. So this is what we are trying to emphasize here. So over a given time period, let us take one particular year which is 365 days, right. Let us take this point and my 365 to be, let me call this as 0 to 365 days, let me call this as 1 year, right. So in 1 year you can see how the degree of saturation varies. Again this is hypothetical, there will be like minor variations. Let us say for example it is 100% or it is 60%. Depending upon the degree of saturation, we have already seen how much is the variation in the resilient modulus, right. So ultimately there is a substantial variation in resilient modulus, and that has to be taken into account. Let us say at this point when the degree of saturation is high, the resilient modulus is at least 50% of the resilient modulus at optimum moisture content, and let us say that this is my MR optimum. I am just hypothetically saying that this is my MR optimum. So at 60% degree of saturation my resilient modulus is 100% of MR optimum. Now when the pavement is loaded, in this condition when the subgrade is fully saturated, the ability of the soil to take up the loads is reduced by 50% compared to another point in time when it is at the optimum moisture content. So assuming a single value for modulus throughout the time period will cause lot of variability in the strains that we are evaluating. It will underestimate or overestimate the total deformation that we expect in a pavement. This graph also shows the degree of saturation during different periods. During winter you can see that it is less because it is cold but the rainfall is less, and during fall season you can see it is relatively higher. During summer probably this is where the rainfall has been higher, so the degree of saturation is higher, and so on. For different seasons they have quantified the degree of saturation and how the degree of saturation varies with the depth. You can see here, maybe if I cross this particular point, right, which is 100 centimeters, the degree of saturation, the variation is less than 5%, right. So we should be taking into account of all of this only up to a particular depth, and beyond that we can neglect the effect of the degree of saturation due to precipitation. So now what is the variation of resilient modulus with the degree of saturation? From another study we can see here. This is the equation which is computed for this particular case, again how the resilient modulus varies with saturation. So when it is 100% you can see it is about 10 megapascal, and when it is 60% it is 130 megapascal. So there is a substantial difference as we have been emphasizing before. This is again from the same study which we are discussing now. Similarly, the variation of resilient modulus with deviator stress at different saturation conditions is also given, right. So we have seen already how resilient modulus varies with deviator stress and how it varies with confining pressure. So this is also going to have a different influence depending upon the degree of saturation. For 60% saturation this is the slope, whereas for 100% saturation this is the slope. You can see there is not much of a change in the slope that you can see here between these two states until a point here. Again the point of inflection varies with degree of saturation, but the slope, these lines are seen to be offset by a constant distance, which shows that the slope will more or less remain the same. So for both these cases the slope remains the same, but this point of inflection is shifted depending upon the degree of saturation. Similarly, we are also seeing the variation of resilient modulus with depth. Previously we saw the degree of saturation, now the variation of resilient modulus with depth is quantified from this study. So you can see for during a given season, right, so it varies from season to season, and for a given season how it varies along the depth, right. So you can see the maximum variation is seen during fall and during winter, wherein there is about 10 to 45, right, 35 megapascal variation in resilient modulus during winter and about 30 megapascal variation during the fall season. Again, all this data is for a particular location, for a given type of soil, for a particular rainfall characteristics, for a particular drainage characteristics and so on. So, this entire graph, the set of constants, the trend, everything is subject to variations depending upon the specific conditions in a given location. So, ultimately the effect of all of it, especially the freeze and thaw on the strain in pavement is quantified. You can see here, this is the vertical strain on the top of subgrade, right? We have a subgrade layer. So, what is the vertical strain on top of the subgrade and how it varies over a specific time period. So, it is given over different weeks, right? We have 52 weeks, which is a given calendar year. So, there are different color lines given here. Let me show you what these are. This is with spring thaw, after spring when there is thaw in the pavement. This is without thaw. Similarly, this is first freeze, this blue line, this red line is first thaw. So, this is freeze, this red line is thaw, this green line is maximum freeze, this orange line is full thaw. So, it has started to freeze at this particular point and the maximum freeze is observed at this particular point, and at this point it has started to thaw and the maximum or the full thaw is over during this period, right. Now, we can see how the vertical compressive strain on top of the subgrade varies for a case with where there was thaw experienced and for a case without thaw. So, you can see here, once the freezing sets in the soil, the vertical strain has substantially reduced. You can see here, right. There is reduction in the vertical strain, and during the period of maximum freezing condition, you can see the vertical strain, and once there is thaw, right, once it has started thawing, we saw that there are weak zones created in the pavement because of the thawing effect. So, the vertical strain increases substantially, then it reduces or it kind of remains constant, and once the full thaw is over and the water has been drained and evaporated, the strain reduces and then it keeps varying, right. So, this is the effect of freeze and thaw, the formation of ice lenses on the strain on top of the subgrade. So, similarly, you can see with spring thaw, the strain shoots up immediately after the thaw period, whereas when there is no thaw, the increase in strain is very less, right. So, the thaw period, when the ice lenses defreeze and more water is present into the system, there is, for a certain period of time, there is a substantial increase in strain. So, all these effects we have to take into account if we want to precisely quantify the strain response in a pavement system, considering the impact of the environmental effects. So, let me stop this lecture here. In the next lecture, we will talk about the effect of temperature. Again, there we are going to talk about the pavement temperature, because that is what directly influences the modulus and what is the effect on modulus. Thank you.